Right, brand new topic to start today, guys. So you got your textbooks on Friday, and I believe some of you've gone through them already. Okay, so we're going to look at mechanics today, right? And in a nutshell, mechanics is basically taking all of the mathematics that we've learned so far and applying it in a practical application. Okay, so why we learn to study quadratics and trigonometry and differentiation and integration, right? We're going to now use them in a real life situation, okay? So one of the first things and first concepts we're going to look at in mechanics is displacement and velocity, okay? So they are two things that go together, right? Which are very similar to two concepts that you've actually already dealt with before. Okay, so we're sort of going to draw up a differences table for these concepts. So if I put on this side over here, I'm going to put distance. And on this side here, I'm going to put displacement. So let's have a look first at the differences between distance and displacement. Right? They are both a measurement in some senses, all right, except they have two very big differences. Okay? So distance is something that we're all familiar with, the distance that we travel from A to B, right? Whether we walk there and back, right? The most important thing about this is that it is a scalar amount, okay, or a scalar quantity, right? And that just means that it only has magnitude, right? So in your book, they have the English nursery rhyme of the grand old duke who had 10,000 men. He marched them to the top of the hill and he marched them down again. So if we think about distance, right, as a concept of measurement, if they had to walk 100 meters up the hill and they had to walk 100 meters down the hill, we would add the distance traveled in both directions and we would get the total distance covered, in this case, of 200 meters. Okay, so very important, distance is a scalar quantity. In other words, it only has a magnitude and it's always positive. There's no such thing as I traveled minus 120 kilometers. Okay, scalar quantities only have a positive magnitude. Okay? Now, on the flip side of that, we have displacement. Okay? So very importantly, displacement is not a scalar quantity, it is a vector quantity. Okay? And vector quantities are made up of two different components, all right? They have both magnitude, and the big difference here is vector quantities also have direction. So when we think about a vector quantity, right, a vector is always relative to a fixed reference point or an origin. In other words, when we talk about displacement, right, we have to define where our starting point is and where our positive direction is going to be. All right, so with displacement, we have to define our starting point and our positive direction. So if we take the example that we've just spoken about before, okay, I'm going to draw a nice green grassy hill. And the distance between the start of the hill and up the hill, this distance here is 100 meters, okay? So in terms of directions, if I go from A to B, back to A, right? If we talk about a distance traveled, we will just take 100 meters plus 100 meters, and my distance traveled would be 200 meters. Now, displacement is a measure of location from the fixed origin or starting point, right? And because it's a vector, it has both magnitude and direction. So if, very importantly, if you take displacement in a given direction to be positive, then displacement in the opposite direction is negative, all right? So in other words, our displacement is a measure of how far and in what direction are we from our starting point, okay? So if we take the displacement of our example here, if we go from A to B back to A again, right? The first part of my displacement is positive because we're going to define going up the hill as the positive direction, and A is our starting point. So my first 100 meters will be 100 meters displacement in a positive direction, except when I come down the hill, I'm going in the opposite direction. And because I'm going in the opposite direction, I need to have a negative displacement, right? So I'll be adding minus 100 meters. And so my total displacement will actually be 0, right? And that is exactly what displacement is. It's not a measure of how far you've actually traveled. It's a measure of how far you are from your starting position, right? What distance and what direction are you from your starting position? You can have a negative displacement. That just means that you are further away in the opposite direction from when you started, okay? So the important thing with displacement is we must have defined a starting point, and we must have defined which direction is positive, right? Is going up the hill positive or is going down the hill positive, right? So two very important things there. Right, the next concept that we're going to look at is speed and velocity. So over here we can have speed, and over here we'll have velocity. Okay. So I'm putting speed under distance and I'm putting velocity under displacement for a very specific reason, okay? So Dominic, what can you tell me about speed?
Speed is a scalar quantity.
There we go, because it only has magnitude, okay? So your car can't travel at minus 120 kilometers an hour, okay? It's just not what it does. Even if it's reversing at 120 kilometers an hour, its speed is still 120 kilometers an hour, right? In terms of velocity, you would be going with a negative velocity of 120 kilometers an hour. So very importantly, speed is also scalar, okay?
Mm-hmm.
So it only has magnitude, right? In other words, can only be positive.
Or it's an absolute value.
Or it's an absolute value, okay? I wish you guys had learned absolute values because that's what I would say, but because some of you haven't learned absolute values, I'm just going to refrain from using it. You might see speed sometimes written like this. As Kiana said, the absolute value, right? But we will get to that later on, right? Just for now, just think if you have something that's scalar and it has magnitude, it can only be positive, right?
Yeah. For now, it's still physics.
There we go. Right, let's have a look at speed. Well, we all know the formula for calculating speed, don't we? What is the formula for calculating speed? Speed is equal to...
Isn't it distance times time?
Not times time.
No,
Think about it.
distance
Speed is
over time,
kilometers
distance
per
over time.
hour. Yeah, so it's distance
Over time.
over time, okay? And if you ever think about it, a speed, 120 kilometers is the distance, per is divide by hours per unit of time. So speed is just a measure of distance over time. Now, very importantly, this is the formula for constant speed, all right? In other words, if our speed is the same throughout the distance, okay? Now, let's assume for a moment that we haven't learned differentiation, because you guys could easily, if I gave you a distance time equation or graph, how would you be able to work out the speed at a particular point, Dominic?
If you gave us a distance time graph, to find the speed, you just take at a certain point, the distance over the time.
Which is just the gradient, isn't it?
The gradient, yeah.
Yeah, and if I wanted the distance from a particular, the average speed or the total speed between certain values, what could we do, Kiana? We could just but if I don't have a constant speed, how could I work out my speed?
It's distance divided by time.
Right. Well, unless I know some very fancy mathematics, I can't work out the actual speed, but I can work out the average speed. Okay. This is like taking the average gradient when we differentiate. We're not getting the exact gradient, we're getting an approximation because we're measuring between 2 points, okay? So if I want to work out average speed, well, I can just take the total distance covered and I can divide that by the total time. So in other words, if my speed was changing all the time and I didn't want to go and work out the speed for each interval, or for instance, if my speed, my distance speed, so let me give you a quick example here. Let's draw a little miniature one. Oopsie, you know, skew line, straight line. Right, if your distance, right, this is distance time. If that graph looked something like this, would you say, Zara, that that is a constant velocity?
No.
No, because we can see the gradient is changing all the time, okay? Now, we actually do know how to work out the average speed because we could just integrate and find the area, right? But if we didn't know that yet, right, the only way we could work out the speed is by taking, well, the total distance that we've traveled and dividing it by the total number of times. That will give us the average speed. It won't give us the actual speed, because if you think about it, the speed was never the same at any point. Okay? It was constantly changing. Okay? Who can tell me what kind of graph will give you a constant speed? There's only one.
A linear
equation,
a linear graph?
If we had, for instance, a linear line that has constant speed. And so when we calculate the speed, it would be the actual speed, okay? Right, let's jump across the fence now and let's look at velocity. So what is velocity going to be, Troya? Is velocity a scalar quantity or is it a vector quantity?
Isn't it a vector quantity?
It is indeed. Okay, very importantly, velocity is the companion to speed, except instead of just having magnitude this time, just like with displacement, right? Velocity has both magnitude and direction. Okay, and very importantly, just like with displacement, we have to specify which direction is positive velocity. Okay, in other words, in your car, we define going forwards as having positive velocity and going backwards or driving in the opposite direction as having a negative velocity. Okay. So if you have a look on page 4 of your textbook, okay. If we compare velocity and speed, all right, you can see that in the same way that we can calculate speed with distance over time, right, velocity is just equal to displacement over time. And you can clearly see, because velocity is displacement over time, right? Because we are using a scalar, or sorry, a vector quantity, we are getting a vector quantity out. Right, Zara, how would we calculate average velocity?
It would be your total change in displacement over the total time.
Here we go. So if we wanted average velocity, whoops, yeah, forgotten to see that. Right, I like the word that they've used in the textbook. They use the word net change in displacement, okay? And that's all over total time. So Dominic, if I walk up a hill at 5 kilometers an hour and I walk down the hill at 5 kilometers an hour, what's my average velocity?
Your average velocity will be 0.
There we go. Why? Because my displacement was 0. Okay.
Yes.
And as bizarre as that sounds, that is what your average velocity would be. Okay. What would my velocity have been up the hill if it took me 5 minutes to walk that 5 kilometers?
Will be 1.
Oh, that's a bit unrealistic. Okay. 1 kilometer per minute. That's
You'd be going really, really, really slowly, like maybe just like even slower than a leisurely stroll. You'd be crawling up the mountain.
There we go. All right, let's quickly have a look at that, the Running Man guy quickly. All right, if you have a look on page 4. Okay. I know it does seem quite silly to look at it in this way, but it's a very nice idea just to confirm to you the differences between distance, displacement, speed, velocity, all right? Because sometimes when you're working with displacement and velocity, you have to think about it for a second, because sometimes when you get a velocity of 0, it makes no sense until you remind yourself exactly what displacement is, okay? So here we have a guy doing a fitness test, right? And he's running backwards and forwards between the length, well, I think it's more the width of a football pitch, because I think the length of a football pitch is 100 meters, not 40 meters. Okay, he starts at the center and runs to one end of the pitch changes direction and runs to the other end, right? He runs at a constant speed of 4 meters per second. Now, the important thing here is, what two things do I have to tell you, Keanu, when we're talking about displacement or velocity? What two things do I have to give to you when I'm talking about displacement and velocity?
Whether it's positive or not.
Okay, the two things are, well, first of all, what is your starting position? If you don't have a starting position, you cannot calculate displacement, right? The whole principle of displacement falls around the idea that we have a starting position. And because we have a starting position and because we can go in multiple directions from our starting position, we must also have defined in which direction is positive and negative displacement, right? So we're only going to be talking about velocity and displacement in 1D, all right? We're not going to be talking about it in multiple dimensions, which it can gets much more involved. So for now, we're just going to stick to very simple positive and negative displacement or positive and negative velocity. So here we go. We're going to draw this guy in his, oops, really doesn't want to give me a line today. Right, here we have the width of the football pitch. Okay. And over here, we have the center, which doesn't look very centered to me. We'll call that. So the first thing that we're giving is, this is the starting point here. Okay, we have the starting point in the middle. We're going to define going in this direction as positive, and we're going to define going in that direction as negative. So in the first diagram, they tell us he has traveled a distance of 10 meters. So let's move this guy 10 meters to this direction here. So 10 meters is, if this is a total of 40 meters, that means that's about a quarter of the way, or halfway to the one end, right? What would his displacement be, Twaya, from his starting point? Remembering that displacement has both magnitude and direction. Well, first of all, if he's starting and if he's moved 10 meters away from the starting point, what is the magnitude of his displacement? How far is he away from his start? He's 10 meters away, right?
Yeah.
And we don't write it in mathematics, but he's actually plus 10 meters away from his, because he's gone in the positive direction, okay? Right, they gave us his speed. He had a constant speed of 4 meters per second. What would his velocity be at this point? Remember, I told you it's constant speed, so, or constant velocity, so it's going to remain unchanged.
2.5. No, wait.
It's just going to be 4 meters per second. Okay. Remember, his speed's constant. It doesn't matter where he is, he's running at exactly the same speed. Now, technically, you could go and work out how long it took him to run that 10 meters, couldn't you? If you wanted to, but we don't have to. Okay, in the second diagram, he has traveled to the end of the pitch, right? So in the second diagram, he has started from the starting position. He's run all the way to the end. He's turned around and he's run 10 meters back. So Zara, what's his total distance that he's covered? Not displacement, what's the total distance that he's run?
It will be 10, okay, then 30.
30, yeah, he's run 20 meters to the end, right? So this is 20 meters and 20 meters, right? So he's run 20 meters to the one end and he's run 10 meters back. He hasn't quite made it back to the starting position, right? He's kind of halfway there. Kiana, what's his displacement?
His displacement is just 10.
His displacement is?
10.
Correct, right? Because he is still 10 meters from his starting position. What would his velocity be at this point? At this very moment right here, what is his velocity as he's running back to the starting point?
-4?
Minus 4 meters per second. Right? Because he's not running in the positive direction, right? We defined as that way. If he's going in this direction, he has negative displacement and velocity. Okay, one final one. Let's say he runs all the way from the starting position. He runs his 20 meters in that direction, and he runs 30 meters in the opposite direction, right? This being the starting point here. Right, Dominic, what would his total displacement be? Remembering that
total
displacement has both magnitude and direction. Well, think about how far is he away from the starting position?
Well, he's
this distance here, isn't he?
Yeah,
So if
he's that
run,
distance away.
So he's run 10 meters past the starting point in the opposite direction. So what would his displacement be?
-10.
-10.
Yeah, it'd be -10. It wouldn't be positive because he's going the other way.
He's basically run, and if you think about it, he ran up the hill, then he ran down, he tripped over, and he's not where he started, he's past where he started, okay, in the opposite direction. What would his velocity be at this point, Dominic? Remembering he's still traveling in that direction.
Still traveling in that direction.
Yeah, and it's
then his constant, then his velocity would be, wouldn't that be -4 meters per second still? Because he's
absolutely
still negative.
Because he's still running. We have defined that if he runs in that direction, it is negative, all right? Just because of the fact that we've defined it like that. Okay, and finally, right, if you have a look in the textbook, the last one, he's turned around again. Okay? He's gotten to the other end of the pitch and he's running forwards now back to the starting point, right? Because he still hasn't got back to the starting point and because he's still on the negative side, his displacement is still negative, except this time he's running towards the starting point in the direction that we've defined as positive. And so he has a positive velocity again of 4 meters per second. Okay. We all happy with that? Nice and simple, nice and easy?
Yep.
Let's quickly do the examples in the textbook. They're, for a lack of wanting to be condescending, very, very easy. Okay. I just want to define for you guys quickly. I'll just move this guy out of the way. What's the formula for speed, Keanu? Speed equals?
Distance over time.
Right. What is the symbol for displacement?
P.
You physics people, what is the symbol for displacement? It sucks because it's very similar to something else that you've learned.
It's P.
S for displacement.
Oh, it is.
Well, velocity is displacement over time. So you have to be very careful. This is speed.
I'm thinking of rho.
This is distance. The only guy that remains unchanged is time, right? But you must be very careful when we're talking about velocity. It's not speed over time, right? That would be acceleration, wouldn't it? Positive acceleration, right? This S stands for displacement. And this is time. So using that wonderful bit of information, Toya, you can do this one for us, nice and easy. A car travels at 9 kilometers in 15 minutes. Find its speed in meters per second. What's the first thing I need to do? I want meters per second.
Well, it's asking in meters, so don't you change the 9 kilometers to meters?
Correct. What's 9 kilometers in meters?
9,000 meters.
There we go, 9,000 meters. I have 15 minutes, right? I don't want minutes, I want seconds. So, Zara, what's 15 minutes in seconds for me quickly? About 900, isn't it?
Yes, that's 500.
Okay, right. We want to work out speed. What's the formula for speed, Dominic?
Distance over time.
Distance over time. So we have 9,000 meters divided by 900 seconds. And that gives me a speed of 10 meters per second. Okay. I cringe in the textbook. They've asked you for speed and they've given you the formula for velocity. Okay. Right, let's grab the next one quickly. On a scale of 1 to 10, what's the difficulty? 10 being difficult, 1 being easy, minus 10 being super easy.
Minus 10.
It's, yeah, around about minus 10. Hey. Okay, next one.
Yeah.
A cyclist, okay, this is where the questions can start getting a little bit tricky, so you just have to be a little bit careful. Right? A cyclist travels at 5 meters per second for 30 seconds, then turns back, traveling at 3 meters per second for 10 seconds. Find her displacement in the original direction of motion from her starting position. So we have 2 displacements that we need to work out and combine, all right? So, Kiana, what's my formula for displacement? If velocity is equal to displacement over time, what is displacement?
Velocity over time.
Not over time.
No, velocity times time.
So displacement is equal to velocity times time. And I've got 2 velocities that I have to work with. And because they're in opposite directions, I need to treat them individually. So I'm going to look at the displacement of the first one. Okay, that was 5 meters per second for 30 seconds. What's that going to give me? 150 meters, right? So if I've defined as that going in that direction as positive, right? My second displacement, right? What will my second velocity be, Toya? Will it be 3 meters per second or minus 3 meters per second? because I'm traveling in the opposite direction now.
Minus.
Right, minus 3 meters per second for 10 seconds. This is going to give me minus 30 meters. So my total displacement will be equal to positive 150 meters plus minus 30 meters. That's going to give me 120 meters displacement. So she's 120 meters from where she started. Okay. Very quickly, Zara, what's the distance that she's traveled in total? The distance, not the displacement, the distance.
Her distance would be 180.
Very good. And that's her total distance. Right. Just one more to go. Right, this is where we can use some of our algebra tricks. Right, if we do cut out, just quickly log back in for the last 5 minutes.
Okay.
Right, it'll be quick, promise. Right, a cyclist spends some time of her journey going downhill at 15 meters per second and the rest of the time going uphill at 5 meters per second. In 1 minute, he travels 540 meters. How long will he have gone or will he have spent going downhill? So very importantly, are we talking about displacement or are we talking about distance? Kiana, what would you say? Are we talking about displacement or distance here? That 540 meters, is that going to be distance or displacement?
Oh, that's distance, yeah.
Distance, okay? So we have to be very careful when we are going to set our equation. Right, the first thing we need to do is, because we don't actually know how much time this person's gone up the hill and down the hill, we have to just leave it as a variable, all right? And we're just going to use the variable t because that is the variable for time, okay? And we're trying to find how long this person is going downhill. So we will say going down the hill is equal to t, okay? This whole travel only takes 1 minute, all right? And if you have a look at our equation, we are all the amount of velocity we are given are in meters per second. So Dominic, how much is 1 minute in seconds?
Um, 1/15?
1 minute in seconds is just 60 seconds.
Oh, okay. I thought you meant 15 minutes. Okay, okay. So,
So
1 minute and 60 seconds.
Going up the hill, he spends t amount of time going up the hill. So how much time does he spend going, well, sorry, down the hill? How much time does he spend going up the hill? Kiana? Well, if it's 60 seconds in total, if he's going down the hill for t seconds, then he's going up the hill for 60 minus t seconds.
Now we've got an equation we can use.
Yeah.
We can put 540 equals t plus 60 minus t. Yeah.
So yeah, from here now we can solve. If our total distance covered is just the sum of the two displacements, right? We can calculate them as well. He spent at 15 meters per second for t seconds. And he went 60 minus t at 5 meters per second. Okay. And this is just a simple linear equation which we can solve very lightly with our eyes closed, right? So this will be 540 equal to 15t plus 300 minus 5t. That gives me 10t equal to 240, t equal to 24 seconds. Okay, and all I've used here, this was just the sum of two displacements. So I said the total displacement was equal to the two together. And these guys are just velocity times time. Okay, so this here, the velocity was just this portion here. And your time was what we calculated there.